So in this video we want to look at the first law of thermodynamics and the ideal gas law. Right? So first law of thermo and ideal gas law. And to introduce the first law of thermodynamics, I want to tell you a little bit about an experiment that was done a couple of centuries ago by a man by the name of Joule, and he showed that temperature was related to the amount of energy input into an object. Okay, so his apparatus was something like this. He had a bucket of water with a pulley attached to it, and the pulley was attached to a rod, and the rod had some fins on it, and he stuck a thermometer in here. It's not a very good thermometer, but you get the idea. Right, so there's a thermometer, and there was a string attached to this pulley, and that string was attached to another pulley connected to the table, and that string held a mass. And when this mass was let go, it would turn this pulley and it would turn the paddle wheel, and that paddle wheel would of course stir the water. And by conservation of energy, you can say that the amount of energy that this mass gained, the amount of energy that that mass gained, would be equal to the amount of energy gained by the paddle wheel and therefore by the water. You're introducing energy into the system. And he noticed, let's say that maybe the temperature was right here at the beginning before he let the mass go, and then after he let the mass go, the temperature rose some. And he did this several times, and you can then say that introducing mechanical energy into a system increases its heat, or gives heat to the system and therefore increases its temperature. And you can do the same thing. You experience this if you've ever drilled, especially into a really thick piece of wood or into concrete or something like that. Your drill bit comes out extremely hot. And so this is a different type of energy you're introducing into the system. Right? This energy is not exactly kinetic energy. The block, of course, is getting kinetic energy, but it's not kinetic energy that you're introducing into the system, nor is it potential energy in the sense that we've talked about before. It's a new type of energy, and we call this internal energy. So internal energy is really the energy that's associated with temperature. And what is internal energy at its root? Well, in a normal glass of water at room temperature, you have molecules, H2O molecules running around in here, and they're moving around, but they might not be moving terribly fast. On average, they'll have velocity vectors that are about the same length, and they'll be in random directions. So they'll be colliding with each other, but just more or less kind of moseying around and whatnot. Just kind of moving here and there. But if I then put that pan of water on a hot plate and crank up the temperature, so we're going to crank up the temperature here. It's going to turn real red, the hot plate is, and then the temperature in the water is going to get quite high. And in that case, instead of having small velocity vectors here, these individual atoms are going to have very large velocity vectors. So I'm going to have an atom here, 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 and here, but now they're going to have extremely large velocities. And they're going to be moving around and colliding with each other and whatnot. And so it is this increase in the motion of these molecules that if you were to dip your finger in here, you'd say, ouch, that water's hot. It's because these molecules now have more energy, but the jug of water or the can of water or the mug or whatever the water's in the pan, that pan doesn't have any kinetic energy, so we can't say that the water itself has kinetic energy. We just simply refer to this increase in energy as internal. Okay, internal energy. So what the first law of thermodynamics says that the change in internal energy, we use U for internal energy, the change in internal energy is equal to any heat added to the system minus the work done by the system. Okay, so here heat added to system and W is the work done by the system. And you might be saying, well, gosh, how can the system do work? Well, imagine that you have a cylinder with some gas in it, and that gas is exerting some pressure all over the place because the molecules are moving around randomly, and so then you put a small flame underneath that canister. That doesn't look a lot like a flame, but we'll see if we can do a bit better job here. Well, my artistic skills aren't all that great, but that probably looks just a little bit better. So you put a flame underneath the canister and let it heat up. And what happens inside? Well, of course, the gas molecules get a big boost in energy after a while, especially the longer you hold that cigarette lighter there, the larger these velocity vectors are going to get. And they're eventually going to increase pressure. So the increase in pressure can move this piston outward. So the piston might move a bit outward. Okay? And because the system has pushed the piston, that means the system has done work on the piston. So the total change in energy, in internal energy in this system, is going to be equal to the total amount of heat added by the lighter minus the work that it did on the piston. Okay? So that is the first law of thermodynamics. Now you also may be asking, what if we didn't put a flame under here, but what if we put some ice cubes? Right, so what if we put some ice cubes under here, or actually, more importantly, put the ice cubes on the canister itself and sucked some of the heat out? What would happen then? Well, it would also, what would really happen is really dependent on how movable the piston is. But since you're taking energy out of the system, right, because heat would flow from the canister to the ice cubes and help melt them, in that case, Q would be negative, and if the piston moved inward, then the amount of work done by the system would be negative, but that negative sign would be canceled out by this minus sign. So you'd get positive work and you would get negative heat, and it would just depend on how much those two balanced or didn't balance as to whether the change in internal energy would be positive or negative. So your delta U, your change in internal energy, can be positive or negative. All right, I wanted to make that point explicitly clear. Now let's turn to the situation where we have a simple canister and we've got some gas inside. And instead of doing something to the gas inside by either heating it up or cooling it down, let's actually exert a force on the piston itself so that we compress the gas by some amount, right? So we've pushed the piston in by this much, and that means the gas is going to be much more compressed. Now, have you changed the internal energy of the system? And the answer is, in general, yes. Okay, in general, yes, you've increased the internal energy in the system, but that answer is also somewhat dependent on the circumstances. Okay, it's somewhat dependent on the circumstances. Now, let's let this distance that we've pushed the piston in, we'll note that as D. Okay, and the piston is going to have some area associated with it, and let's let the force that we've pushed the piston in with be denoted as F. Now, the work that we have done by pushing the piston in, remember that force is equal, or work is equal to force times distance. So the force that we've pushed the piston in with times the distance that we've pushed the piston in with is going to be the work. All right? So that is work done to the system, so that would be a negative W in the first law of thermodynamics. Now, go back to the last chapter and remember that the force that we've pushed this in with times this area has caused a change in pressure. Remember that pressure is equal to force over area. And so if I solve this equation for force, I can plug it back in to find out how much work I've done. And so I find out that the force is equal to pressure times area, so that the work is going to be equal to pressure times the area times the distance that I've pushed it in. But look at this term, AD, right? So if I look at this area here, the space that I have pushed in with my piston on my cylinder, that encompasses a volume. And what is that volume? Well, that volume is going to equal the distance that I've pushed it times the area of the piston. So I've changed the volume of the gas from this initial volume to this final volume here. I've changed it by an amount, delta V. And that delta V is going to be this area times the distance I've pushed it in. And so my work, the total work that I've done, is going to be equal to P times delta V. And exactly what happens with the internal energy is going to be dependent on what type of process I cause this to be. So there are several different types of processes that you can have when compressing gases like this. Okay, so the first is adiabatic. And an adiabatic process means that no heat is transferred to or from the system. So imagine that I start here and compress the cylinder fast enough that no heat is able to go into the system or escape the system, and that means that in an adiabatic process, since no heat is transferred, Q is 0. And because, if we go back again, I'm doing work to the system, that means that the system is doing negative work, and that means I can write my first law of thermodynamics as the change in internal energy is equal to Q minus W, but again Q is 0, so 0 minus a negative work. So the change in internal energy is going to be equal to the work that I do to the system in an adiabatic process. And that makes sense because if I compress the gas, we all hopefully know that the gas will become under more pressure, the temperature will increase inside, but again in the adiabatic process that temperature is not allowed to escape, so that temperature increase inside goes into increasing the internal energy. The atoms become more excited, and so this is the condition for an adiabatic process, delta U equals W. You can also have what's called an isobaric process, or let's start with isothermal first. So we can also have an isothermal process. And what this means, iso means same, and thermal means temperature. So here in your process, the temperature of your substance doesn't change. And even though no heat was allowed in or out of the system in the last case, the temperature inside increased as a result of the pressure increase. But in this case, the temperature is not allowed to increase. And you can do this by both pushing the piston in our example, which will increase the temperature inside while holding maybe something like an ice cube, or putting the piston in an ice bath or something like that to take the heat out as soon as it comes in. So the temperature of the gas is not allowed to change. So it's not allowed to increase or decrease. And what that means for the first law of thermodynamics is that because there's a very direct relationship between the temperature of an object and its internal energy, that means if the temperature is not allowed to increase, delta U must be 0. And that means that whatever heat we put into the system must be counterbalanced by some work done by the system. Okay? So for an isothermal process, we're going to get that the heat that we add to the system is going to be counterbalanced by work done by the system. Okay? And finally, we can have an isobaric process, and iso again meaning same, baric in this case meaning pressure. And an isobaric process is probably best illustrated with an example. And so let's talk about the hot air balloon. So when you first have a deflated hot air balloon, so here's the basket, sometimes called the gondola, and here's the burner, and here's some strings, and you have a deflated balloon that just kind of lies on its side here. But as you put fire into the burner, the balloon, the balloon will start to blow up. It'll expand. Now, here's the key. The number of molecules in the balloon don't change. Also, because the balloon is expanding as the molecules gain heat, that means that the pressure inside the balloon and the pressure outside don't change. So no change in pressure. But why does the hot air balloon rise? Because you have, if the balloon were deflated, and this time I will move over here. So if here's our gondola and here's our deflated balloon, we have all sorts of molecules in here. Okay, so we have, by my count, I think I put 24 molecules in there. I want to put exactly the same number of molecules in the inflated balloon so you can see what happens. So the number of air molecules doesn't change, but when I turn the Bunsen burner on, right, when I turn the Bunsen burner on, or the propane burner really, okay, I just call it a Bunsen burner, but it's really burning propane. I guess it is a giant Bunsen burner is really what it is. So you put your fire in here and your balloon expands out like this. Now those same number of molecules are spread out over a much larger volume. Okay, so there's 24 molecules, and they're spread out against a much larger volume. And so the density decreases. Below normal atmosphere. Or below normal atmospheric pressure, if you will. And because the pressures are the same, no air is rushing in and no air is rushing out, so that, again, the number of molecules don't change, but the density has decreased, and so now, because the density decreases, the balloon will rise until the density in the balloon matches the density at that altitude. And so that is what causes the hot air balloon to rise, and that is why it is also an isobaric process. And isobaric processes also take advantage of what's known as the ideal gas law. And the ideal gas law says that if I have a gas that behaves ideally, which is actually often not a bad approximation, if not almost darn near exact, and the ideal gas law says that for an ideal gas, the pressure of the gas times its volume is going to be equal to two funny constants, N, K, times the temperature. Now, the temperature here must be in Kelvin for this equation to work. And here, N is the number of molecules in the gas, and K is a constant known as Boltzmann's constant. Okay, and I actually don't remember the value of K off the top of my head, but it's often not necessary if you're going to be doing comparisons between two different objects of different pressures and volumes and temperatures. So for example, suppose that we have a container of gas, and in that container our initial volume is 4 liters, right? And let's say our initial temperature was 6,000 Kelvin, or 600 Kelvin. Let's use 600 Kelvin. And let's say that we shrink the box down to a volume of 1 liter, and it has a final temperature, or we want to know what its final temperature is going to be. But we do this under the assumption that P doesn't change in the process, or the pressure doesn't change in the process. So what we can do is say that our pressure times our initial volume must be equal to N times K times our initial temperature. I'm going to rewrite that K. And our pressure times our final volume must be equal to Nk times our final temperature. Now, no gas leaked in or out of the box, so I'm going to seal up that hole there. And so N didn't change, and Boltzmann's constant is just a constant, so this value Nk is the same for both of these boxes. So what I can do is say that P times Vi divided by Ti is equal to N times K, and that I can do that over here too. P times Vf over Tf is equal to N times K, but that means this expression and this expression must be equal. So I get P Vi over Ti is equal to P times Vf over Tf, and notice that in this case my pressures are the same in both cases because I'm holding the pressure constant, so I can solve these this equation rather for Tf by multiplying Tf up onto this side, and then essentially cross multiplying and dividing is what I'm doing. So if I multiply Tf over here and then multiply by the reciprocals over here, I'm going to get that Tf is going to be equal to Vf over Vi times Ti. And this will be Vf was 1 liter, Vi was 4 liters, and Ti was 600 Kelvin. So I'm essentially dividing my temperature by a fourth, or I should say dividing it by 4, multiplying it by a fourth. So 1/4 of 600 is going to be 150. So in this case, even though I'm compressing the gas, because I'm holding the pressure constant, the temperature then must decrease. And notice, you might have been able to guess that from this equation. If this is held constant and this side goes down, there's nothing for temperature to do but go down. It must go down as well, right? Now, to finish off this chapter, I want to talk about the idea of conduction and that of convection, because these are the two ways through which heat is transferred, typically. Okay, so conduction is the process by which heat flows through one object I can't not spell today. One object to another when they are in contact and at different temps. When they're at different temperatures. So imagine that I have a table here and I have two objects, and let them both be metal, but one of them has been in the furnace and it's really hot, it's red hot, and the other block is at room temperature. What will happen is that I have a lot of Q in this object, and that Q, if these two are placed in contact with each other, that Q will flow to the cooler object until their temperatures are equalized. Okay? So conduction is when heat flows from one object to another when they physically touch each other and they're at different temperatures. If they were at the same temperature, of course, the heat wouldn't flow between them. Convection, on the other hand, is the motion or the transfer of heat, if you will, by a fluid in motion. And this is the principle behind central heating. In central heat, you have a room and you have a vent, and that vent can either push up hot or cool air. It just depends, but let's say it pushes up hot air. So the air that is initially pushed out of here is going to be hot, and it's going to circulate through the room because hot air rises, but as it moves through, it's going to eventually cool down because it transfers its heat to the room and will enter back into the vent as slightly cooler air, but the net effect is that the room will get incrementally hotter. And that's because as this hot air transfers its heat out of the current flow, that heat is being transferred into the room itself. And that transfer is what cools that air off, and then that air sinks back down and goes back down into the vent. So this hot air will indeed transfer heat into the room, and that's what makes the room hotter. And that is what the idea of convection is all about. So that is all about Chapter 10, and in the next video we'll look at Chapter 11 and the second law of thermodynamics. We'll see you then.